Okay, this video is going to be about the 4-wire or bipolar stepper motor. Really wanted to figure out how one of these things work. I've seen a lot of write-ups, quickly glanced at a bunch of stuff, and descriptions never seem to be very thorough or very clear. I never came away with a good understanding. The one best place I think to find data about these is on YouTube, of all things, and one of the best videos I've found is this one you see on the screen here. You should watch that. It will really clarify the inside of a stepper motor and how they work. So it's a pretty interesting video. Well, I found this one at one of my local surplus electronics places. It's just a little can stepper motor. Obviously probably came out of some kind of drive, maybe even. I have no data for it. It's got a number on the back, A87DT. I've searched that number, and I actually have found it as part of a larger part number. And those turned out to be stepper motors, all right, but they were big, open frame, square frame motors. So definitely not this one. I've also got a little, from a servo motor kit, I got one of the arms and mounted it on the shaft here so you can, we can see it turn a little bit easier. So what you got is the can and 4 wires and no data. So to basically figure out what you got and what to do, let me find my probes here. You're going to home out each set of wires and find your pairs. So there's going to be 2 wires that ring together with some resistance. This one has 20 ohms on the yellow blue, and so the other pair is going to be about 20 ohms, hopefully. If I can get on there. And so that's your other pair. And basically, you can try to limit your current where if you need additional current limiting over 20 ohms, and probably will, you know what you're working with there, and you know where your pairs are. Now when you hook it up to a known good pair of H bridges, what you can do after you find your pair, you just put the one pair on one H bridge and one pair on the other H bridge. It doesn't matter. You don't have to worry really how you're hooking them up, except that the pairs stay together on a single H bridge. Then you, if you have known good code, you start driving your motor, and if it advances smoothly and with the same increment per step and doesn't back up and go forward, and it goes in the direction you want, well, you are lucky. But if it does step erratically, then just pick any pair at random and swap the leads of that one pair, and then it should start stepping uniformly in one direction or the other. Now if it doesn't step in the direction you want, you can just lift each pair and swap pairs between the H bridges, and then it should turn in the correct direction. And that's all there is to figuring out your wiring. So we need to look at the topology of the motor and how we're going to drive it, and look at some of the H bridge circuitry. So let's go take a look at the topology first. Alright, I'm going to try to explain a little bit about how a stepper motor is constructed. We've all seen diagrams of stepper motors. I think the most common one has a circle, has a coil like off to one side with 2 wires coming out, another coil on the other side with 2 wires coming out, and that's supposed to be a stepper motor. Well, it really doesn't explain much of anything. It's just a symbol. I think they ought to have in that case, just have a circle with a S for stepper in the middle and 4 wires coming out of the circle. Now a little bit closer to reality is this figure here, figure 1A from the web page. Now in this one, if A is positive, if A plus is positive and A minus is negative, then this end of this coil is a north pole and this end of this coil is a south pole. If we take this to mean the rotor and we take the arrowhead to mean that it's a north pole, then the north pole of the rotor is going to be attracted to the south pole of this coil, and the motor shaft will be aligned like this. Now to step this to the next position, we stop driving A plus A minus and we drive B plus B minus. Now if B is driven positive and B minus is driven negative, then this end of this coil becomes a north becomes a north pole, sorry, and this end becomes a south pole, and the arrow will be rotated counterclockwise to align straight up and down. So that's basically gives you an idea how these coils on the stator work together. However, the rotor polarity is not like this at all. There's only a single polarity at the rotor. And that's because the rotor is magnetized actually along or longitudinally along the axis of the motor. It's the only motor that's built this way. So if you look at the face end, if you consider this to be the face of the motor, then all the poles are south poles, and the far end, at the other end of the motor, all the poles on the rotor are north poles. So this is also a misleading diagram. So this is the closest one I've found that kind of represents what's going on. All these poles on the rotor are south poles. The far end of the motor, all the poles are north poles. Now some motors will be built this way, where you just can look at one end of the motor and all the coils are arranged around the end that's south poles. Now that's a cheaper way to build it, less power, less cost. And some other stepper motors are built that repeat the coil, the stator coils at the opposite end, at the north end, but everything, all the wiring for the coils is just reversed from the south end. So it works the same way, except everything's just reversed. So, but we can get a clear idea what's happening just by considering this end of the rotor. Okay, now to step the motor, A1, A2 are energized such that this pole becomes north. The next pole along its path, it's wound in the opposite direction. So while this pole is north, this pole is south. And then the next one reverses again, and this pole is the north pole, just like this pole is north pole. Then we go around to this pole, and it's a south pole. Now the way it works is, you can see the south pole of the rotor is attracted to the north pole of the stator at this point. Over here, where it's where this coil is a south pole, it's repelling the poles on the rotor, and the geometry is such that the number of poles on the rotor should be 2 greater than the number of poles on the stator. Now this diagram is not drawn that way, unfortunately. This diagram has
2 fewer poles on the rotor. And I'm not sure if any real motors are built this way or not, but the geometry does kind of work out for our discussion here. So while this pole is north and it attracts the south, this pole is south and repels the south pole. But the geometry, because of the number of poles are different, the geometry of the rotor is such that there's 2 poles evenly split along the axis of this south pole. That means that this pole is repelling the stator poles equally because they're balanced right in between. This pole doesn't want to turn clockwise because it's being repelled, and this pole doesn't want to turn counterclockwise because it's being repelled. So it's held in this position by the magnetic field just as much as this pole is held in position by this magnetic field. And that continues on around. We see the geometry of the rotor here at this north pole. This pole is in line again. And if we go around to the next pole, that's a south pole here, it's repelling the 2 evenly spaced poles on the rotor. Now to make a step clockwise, we'll stop driving the A pole and we'll drive the B pole. And just like before, it'll attract this south pole because this is now a north pole, and this one is a south pole, and it repels this, so it helps push this rotor clockwise. And the geometry works out the same. You'll find the center, the split will occur right here, this is a south pole, and it reinforces, just like it did in this situation, it reinforces the position by repelling equally the 2 south poles. And the same thing occurs for all the poles around the circle. So I hope that kind of helps explain what's going on inside a bipolar stepper. Please watch the video I've got linked in, and because it does a much better job of explaining what's going on. So I hope I haven't confused things more than clarified things, but be sure you check out that video I've got linked. Alright, let's take a look at generating our signals to control our stepper motor. And we're going to look at single phase mode first. It's the simplest method, and it explains the basics. However, it's not very much used because it doesn't provide a lot of torque in your motor, but it's a good way to describe exactly what we need to do. So we have our I/O port here, and bit order is significant. Most significant nibble is going to be A1, or any phase really. We're just picking A1. Next will be B1, then the A2, and then the B2. And this is going to facilitate our software having this order. So I have those signals here listed in that order. The first thing that happens is we set A1 to high. Everybody else is low. The next step is when A1 goes away, B1 becomes high. A2 and B2 remain low. Then B1 goes away. A1 remains low. A2 goes high. B2 remains low. The next step, B2 goes high. Everybody else is low. Whoops. Everybody else is low. And out here, and then the cycle starts again. So you get a basic stair-step case. And for turning the motor in the opposite direction, you just generate B2 first, then A2, B1 and A1, and make a nice stair step going the other way. You'll see that on the
oscilloscope. So to make a number out of all these, if we A1 is our most significant bit, so this, the value in this time frame is 8, value in this time frame is 4, the value here is 2, this of course is a 1. Okay, so now I have the binary written for these states, and we can see pretty easily that that each character or each output waveform is the right shift to the previous one. So each time a bit goes from the 8's position to the 4's position, then to the 2's, then to the 1's. And then if we shift this off in software, we usually go into the carry flag, always test carry. As soon as carry goes high, we set the most significant bit of the nibble back to high. And of course the opposite would be just shift lefts. Start at 1, shift left to 2, 4, 8. We have to monitor this bit in a real register somewhere for when the bit shifts into here, and we'll just go back and set the least significant bit and start circulating again. So that's basically how we're going to drive our port with our software, just with right and left shifts, depending on the direction we want to go. We have to be sure we wire our port up in this sequence, so it agrees with our little routine here. Okay, so let's look at doing double phase or full stepping. Okay, here's a signal generation for two-phase or full stepping. We start out with A1 set to a 1, and B1 set to 1. That's the first phase. That gives you a C, which you have written over here in binary. The next step is B1 and A2, which gives you a 6. And the next step is A2 and B2 high, which gives you a 3. And the final step is A1 high and B2 high, which gives you a 9. Return to the next step is return to C, and we just cycle through that. Now, using our shift register scheme that for our I/O port works real great, just like we discussed for the full wave waveform. And basically, this makes a nice recognizable stair step for going one direction. Of course, the stair step would angle up the other way for step in the opposite direction. We'll see that on the oscilloscope when we get to it. Okay, now let's discuss half stepping, or 1-2 phase as it's sometimes called. Now this was going to get a little hairy for the whiteboard, so I decided to do it in a text file and just show it like this. So the first thing we do, we have A1, B1, A2, A2. Those are our register I/O port outputs. First thing we do is drive A1 high. All other outputs are low. Next thing that happens is A1 remains high and B1 goes high, while A2 and B2 remain low. In the third phase, A1 turns off, B1 remains on, while A2 and B2 remain off. Now A2 turns on while B1 is still on. A1 and B2 remain off. Now B1 turns off, leaving A2 on, and A1 and B2 remain off. Now B2 turns on while A2 remains on, and B1 and A1 remain off. Now A2 turns off while B2 remains on, and A1 and B1 remain off. Now A1 turns on while B2 is on, B1 and A2 remain off. Now B2 turns off and A1 is left on by itself, and we see that that's the starting condition. A1 is on with the other 3 lines off. So that ends our cycle, and it turns out there's 8 cycles within here. Now, of course, cycles continue on. Now we need to identify what these cycles are, the drive values we need for them. So A1 here, that's going to be our most significant bit in the I/O port nibble. So that's an 8. Next to turn on is B1, so that makes the output a C. Then A goes off and leaves B on by itself, so that's going to be 4. Now A2 comes on with B1, and that's a 6. And now B1 turns off, leaving A2 on. That's a 2. We now have B2 coming on with A2, and that creates 3. Then A2 turns off, leaving B2 on by itself, which is a 1. And next, A1 turns on with B2 on. That's a 9. And we see B2 turning off here, leaving A1 on. That's a 8. And that's our first, that's our starting condition. So we've gone through 8 cycles, 8C4, 6, 2, 3, 1, 9. And that's pretty complicated. Can't do it with just shifting bits like we did before. The only thing to do, about the cleanest way to do this, is take these values, put them in general purpose registers in this order, these values, and then use indirect register addressing to access these individual nibbles and send them out on port C. So that's how half stepping is going to work on our little project here. Okay, let's take a quick look at the schematic for our stepper motor project. Of course, we have the PIC 16F876. We've got our 2 H-bridge drivers. We've got the star of the show, the motor. We've got some LEDs to monitor a little bit what's going on. Optionally, I'm showing a DL1414 for some output, but there's no code for this, and it's not on my breadboard, so this is totally optional. This kind of takes up these pins so we don't accidentally use them for something else in case we want to add some display a little bit later. We've got our output conditioning for our driving our H bridges, and we've got a set of 4 switches that are connected to AD0, and that's red. These switches are multiplexed by reading various voltages on the with the A to D converter, and then we have a switch for mode. Let's go over these in a little more detail. Here's the A wire H bridge. We got drive A and drive A2 coming in from the PIC, and the output goes to our A windings on the motor. Now each side of the H bridge has 2 drivers that connect the motor to your power supply and ground. So what happens is we drive this transistor high. He in turn turns these 2 transistors on. Current flows from the positive side of the supply through this transistor into the motor winding, through the motor, out the motor winding into motor A2. Current goes this way, this transistor is on, and returns to ground. So that turns the motor in one direction. Drive A2
does the opposite. Turns this transistor on, which in turn turns these two transistors on. Current flows now from the power supply into motor A2 through the motor, back out motor A1. Motor A1 connects here. This transistor is on. Current flows to ground here, and that completes the circuit. And that turns the motor in the opposite direction. Now the components here, these are all small signal transistors. And I ended up driving the H-bridge with 5 volts. It turned out that that works fine. I tried that first and it works fine. So you really don't need H-bridge control at all. You could just use 5 volts. But since I'm demonstrating H-bridge, I'm just going to leave it in here and leave it running at 5 volts. These component values allow just under 200 milliamps to flow through the motor. If you leave the motor on for any period of time, you can feel it gets up above room temperature, but that's about it. It doesn't get very warm at all. But I've only run it for about 5 minutes max, so 200 milliamps may warm it up after a while. These diodes here can be any 1N 4000 series that you want. A lot of people like to use Schottkys here. You can do substitute Schottkys if you want, but actually 1N 4000s are fine. I'm going to have more to say about these diodes in this follow-on video. So now here's the motor itself. Here's the B side, H-bridge, which is just identical in every way, works the same way as the A side. And of course connects to the B side. Now here I've got some LEDs, and they're basically to monitor the state of the inputs to the motor. Now these are not in the order of the register output, so they're going to light up a little differently from the waveform pattern that I've drawn on the whiteboard and that we're going to see on the scope. Basically I put the A's together and the B's side by side, and this is so I can monitor if both the A's come on high, both LEDs will light up side by side, and that'll be easier to see, I believe, than if they were in the order of the drive signals. So basically they monitor the big no-no. You don't want to ever drive both of these inputs high at the same time. If you do, current's going to flow through this transistor, It'll ignore the motor because this transistor will be on and this transistor will be on. So current will come through all transistors, this way and this way, ignoring the motor completely. The motor won't be any impedance to the flow of current, and you'll cook these transistors. And I did it while working on this project. So one thing you can do when you're working with code, lift these pins on your breadboard until you know your code is working correctly, and then you can put them down and drive your motor. And this is just to monitor if you make that mistake. So I figure you can see these, if they're side by side, you can pick them out better than if they were A1 was here and A2 was here, and like the output registers are. So that's why those are wired that way. The next thing is we have a display here. Not going to use that, as I said. The input from the PIC is conditioned. The main feature, this is so the divider here cuts down the drive voltage a little bit to Q1 and keeps it from fully turning on all the transistors in the H-bridge. They're mostly on, but not completely. But the main feature here is these pull downs, and
these ensure that while there's no drive, while you're configuring and power up your processor, before you can configure these pins, that they're no doubt floating. So these resistors pull down the inputs to the H bridge and make sure they don't go high, just like I talked about. So you have to have these to protect your circuit and protect your H drive circuit. The next thing is the switches that control the pattern we generate. I've got 4 switches here, and they're pulled up by this resistor to 5 volts. Every time you press one of these switches, it activates this voltage divider, and it changes the voltages to 4, 3, 2, and 1, and that is read by the analog to digital converter on AN0. So this saves using 4 pins to read these 4 switches. They're multiplexed by the A to D converter. Tolerances here aren't critical at all. This is a big wide margin. The code reads like 3.5 volts, 2.5 volts, 1.5 volts, and half a volt to determine which button is pushed. And you don't have to have very tight components at all, because that's a big margin for the A to D converter. The first switch is a single step clockwise, single step counterclockwise, continuous run clockwise, and continuous run counterclockwise. And then this switch is called a mode switch. It selects between half-step waveform and a full-step waveform. So when this is 0, you get a half-step. This controls half-stepping, and when the switch is 1, open and pulled up, it generates full-step waveform. Of course, we got a crystal running at 16 megahertz. Here's my power. You can see I have 9 volts on my breadboard. I've actually combined these. Both these are tied together, and it's 5 volts only. But as I said, if you run it 9, all it's required is to tie 9 volts to the H bridge, and that pretty much covers all the functions of the schematic. Alright, let's take a quick look at our code for our bipolar stepper. The A port, we're using RA0 or AN0 as analog input to the ADC, and those are decoding our 4 switches. We're going to multiplex 4 switches on AN0. Also, we got a mode switch we have tacked on here, and that's going to tell us whether we're doing full step routines or half step routines. So we set that up by writing tri-state A controller 3F. Everything is an input. Now on port B, we just have a couple of debug ports defined. It's not in the code used anywhere, but we got some equates for that here. And tri-state B, it's set up as those two debug ports are outputs. I write an FC to tri-state B control. Okay, port C is where our drivers for the 4 drivers to the 2 H bridges. They have to be in this order for our code to work. We have A1, B1, A2, and B2. Descending order from RC3 down to RC0. And we write tri-state C control as F0, making those outputs. Everything else is inputs. Okay, setting up our analog to digital converter. All we have to do here is turn on the converter and select the clock source, which is going to be the oscillator divided by 32. and that's pretty much dictated because we're running at 16 megahertz. ADCON 1 needs to be set to 0E, and that makes AD0 connected to the analog, to the ADC input, and it also selects a reference voltage internal, VDD and VSS. And we're going to also need to be sure left justified results are is selected by writing a 0 to ADFM. Use no interrupts. Here in the setup, we do all that setup we just discussed. We have to do a little thing here for the mode switch. Now, what happens is we keep an image of what the mode switch is at all times in a general purpose register called mode image. And when it sees a difference in mode image and what the switch is, the code knows that we just switched over either from full to half or half to full. So this is where we keep track of that. And when we initialize it, we want to make sure they're different. And that's so mode switch reads the switch and compares it, gets a false value, and sets up the conditions to start up in the correct mode. So here we guess at 1, we set mode image to 1. If the actual switch, which is read here, is a 1, we skip this instruction and we clear mode image. That makes them different. If this was clear, we just go ahead and mode is clear, and we set mode image to 1. They're different, so we can go ahead. And this is the final step in our initialization, and this is setting up the half-step control. There's 8 steps required to do half-stepping. They're pretty complicated. Can't do anything like a shift left or right or anything like that, so we just put the actual values in general purpose registers, and what we're going to do is just scan from the first register to the last and loop around to go one direction, or we go the opposite direction. We scan up and loop around this way to go the other direction. The main loop we call debounce and decode over and over. That's all it does. Debounce, make sure a switch is debounced correctly, and it also calls switch read. Now switch read uses the ADC controller, and it just compares. The basic scheme is to compare values just with addres H, and that's the most significant 8 bits of the 10-bit A to D converter, and that's all we need to care about. We're essentially reading in between 1 volt, in between 1 and 2 volts, 2 and 3 volts, 3 and 4 volts, and 4 and 5 volts to get a value. And so there's a whole bunch of margin. The resistor values aren't that great. And so when we find a value, if we don't find a value, we decrement the switch number. And when we do find a switch number, these values are such that you quit decrementing switch number. So when you drop out the end, you end up with the correct switch number. Here's where to decode the value. Here's where we check mode image to see if we've changed the mode or not. And if we do, we set up the proper initialization. For half stepping, we have to set up the FSR, and for full stepping, we just have to make sure that the step image, we start off with the OC, put it in step image, and we just shift that left or right. And these are the full stepping routines. Depending on the switch, we'll either step once clockwise, step once counterclockwise, run continuously clockwise, or continuously counterclockwise. And that's the same for full stepping and half stepping. And here's a little table where we jump to the correct routine. And actually clockwise and counterclockwise for both full and half step. For doing a single step and continuous run, it's the same routine. To do a single step, we call a routine called switch off. And that waits for the switch to be off before we decode the next switch. And for continuous run, we just call it delay routine, and it repeats. Here's where we wait for switch off, which gives you the single stepping, and then the clockwise full steps and counterclockwise full steps. For those, we just have to shift left to go clockwise, and here we shift right to go counterclockwise. And for half stepping clockwise, we go through our indirect register addressing, moving FSR every time we enter this routine, and read the value out using the INDF to W instruction, and we write it to port C. And for clockwise, we're where's my decrement increment? Oh, right here. It's the top. Sorry. Decrement. For clockwise, we decrement FSR. For going counterclockwise, we increment FSR. And then the delay routines. And that's pretty much it. Here's the breadboard for our little project. First of all, we've got the 4 switches here. I've got a little hex switch. Makes it nice and compact to put on here. The resistors are right here. 3 of them are standing up at you, so it's probably hard to see. And the pull-up resistor for the switch. That, of course, runs over here to pin 2, which is the analog input. Of course, the pick. The other switch, the mode switch, is actually this pull-up resistor, and that makes that point high, and I just jump her to ground with a little jumper to make it low, so there's really no switch. Didn't really have the space. Of course, a little bypassing for the processor. Now here's the H bridge layout. 2 H bridges. The on the left of the probe is the A side. On the right's the B side. Top portion is the A1 B1, and the bottom portion is the A1 A2 B2. If you look at, this is kind of a mess to lay out, but what you do if you kind of work on one section, get a nice little arrangement, do one side of one H bridge, and then just get a pattern that works, and then just copy that 3 times, and it makes the other 3 go a lot faster. You just really have to concentrate on doing the one layout. Then you just duplicate it 3 more times. Of course, the motor with the little arm on it, so we can see it go around, and the LEDs, and that's about it. Okay, I guess we're gonna get ready to power this baby up and see how it works. Okay, so we're ready to fire this baby up. Let's turn her on, see what happens. Nothing happens, which is actually good because I haven't flipped the switch yet. I've got the little tweezers here I have to use my hex switch with, and I've knocked this thing out of the circuit so many times using this thing, but it's the best thing I know, and it's going to be hard working around this camera. So anyway, let's try a right step. We'll try a counterclockwise step. Now the first time, it doesn't necessarily, the first time it's not going to necessarily be correct. It might go counterclockwise. Well, there, it is pretty good. Okay. Like I said before, the first two are A1, A2, and the next two LEDs are B1 and B2. And it's not the sequence of the shift register out of the I/O port here. It's I put them together so I can monitor a lot easier that this pair is never on at the same time and this pair is never on at the same time. You don't want that. That means you're shorting out your H bridge. So in every step, every time we do a little toggle on here, we take a step right. And we can step backwards. And we can go clockwise continuously. And I've got this set on pretty slow steps so that we can count the number of steps it takes to go around once. So if we also demonstrate counterclockwise. Get it lined up right at the, whoops, I missed it. Get it lined up. Well, shoot. Get it lined up there. Stop at the top. Now we'll go clockwise and we'll count how many times it takes to go halfway around. 1, 2, 3, 4, 5, 6, 7, 8, 10. So this is 20 steps around at full. This is full step mode. You count again when it gets up at the top here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Okay. And so there we got forward and backward and full step. Now we'll throw our switch, which is a jumper. And if I don't short anything out here, it'd be a miracle. As it goes in the dark. Now we should be half stepping. And I drop my tweezers. And do a single step clockwise. This might not be, this is not going to be synced up either. It could jump in any direction. I took a huge jump that way. There. That looks a little smaller. Now you can see every step it's a mixture of wave stepping or one phase stepping and two phase stepping. So there's two phases. Next step would be one phase. Next step would be two phases again. Next step will be one phase. And this is where it's reading the pattern using indirect addressing of the general purpose registers. And then go backwards. That's half stepping. Okay. Let's try clockwise. And you can see that's a lot smaller. Just had a little glitch there. Count what it takes. When it gets lined up at the top, we'll count steps to get to the bottom. It was 10 previously. 1, 2, 3, 4, 5, 6, 7, 9, 10, 11, 12, 13, 14, 15, 18, 19, 20. So there it's taken twice as many steps. So you get a little bit higher resolution than half stepping than with full stepping. Okay, well, appears to be working pretty well. Let's look at the waveforms on the scope. Okay, since my last video we had some scope shots. I had my Tektronix 465. It has given up the ghost, and I got me a Rigol DS1054Z, and this little thing is great. It's got some quirks and everything, but gosh, for what it does and for the price, I can put up with the slow response here and there, and a few little glitches. They're not major at all. And this is a incredible little scope for the money. I just can't believe it. And having replacing the 465 pure analog, it's like having a logic analyzer almost, and it's just great having the 4 channels. Tell you what. So okay, well, let's look at the signals on our deal, on our stepper motor. I'll do a clockwise, see where it initializes to. We have A1 on top, B1 next, third channel is A2, and the last channel is B2. So we've got A1 high and B2 is high. All channels are on 5 volts. You can see where the labels are. The labels are on 0 essentially. That really helps. Of course, you got the marker out to the side where ground is, or where the reference was set. And having a label really helps too, to identify that. Okay, so every step, got it in roll mode also. Time base is in roll mode. There's the next step. We see it go to A2, A2, B2. Step right again. It's A2, B1 is high. Step again. We got A1 and B1 is high. And step back, just drops back to A2 and B1 high. So letting it run in clockwise mode. Let me turn it down a sweep. So we get our typical stair step. Why is the trigger? Had the trigger over here earlier. And there's our pattern that we expect. Basically forms a stair step heading up from the bottom at a slant to the right, going from bottom to top. Let me get a single sweep so it stops. So there's your typical sweep for clockwise. The way this is wired for a clockwise step, and we'll reverse it. Basically looks the same, except the slope is the opposite direction now. Do single sweep so it'll stop. Now I'll flip over, change mode, and we'll look at half step. Is clockwise half stepping. Now I see see if I can get the can read the code, the 8-bit. One more time, this will get it. Okay, here's our 8. Then C, 1 0 0 1. Oh, we're going backwards. 8 9. That's 9. 9 8 9 1 3 2 6 4 C 8 low 1 back to 9. So there's our half stepping pattern. Okay, well, that's what the signals look like on the scope, just like we drew out on the board. Next time, I'm going to try to look at, if everything goes well and get it hooked up, I'm going to try to measure torque. I'm going to try to see what speed effects there are. If you go too fast, these steppers can overshoot. If you start up, you can miss steps. If you're counting steps, the motor won't necessarily make every step that you send it. So we're going to see if we can demonstrate when that happens. And the last thing is, if it works out okay, I'm going to show you, I'm going to duplicate a video on YouTube where a guy ran a stepper motor straight off a pick. And we're going to try to do that, and we're going to see if we can figure out why he got away with that. Okay, see you next time. Thanks for watching.